Okay, first of all, I would like to thank the organizers. Thanks for the introduction and also for giving me this thing. So it's a pleasure to be back in Uppsala. It's very sunny and the air conditioning is working well in here. So it's a curious coincidence that I shall be talking about counterterms and E77 symmetry in n=8 supergravity. That's about work I did in collaboration with Stefan Stieberger, Alejandro Morales, Michael Kiermeier, Dan Friedman, and Henriette Erwang. And there are also a couple of other papers closely related to this subject, which I shall report on. But before I talk about n=8 supergravity, let me start with the simplest quantum field theory. And that is clearly planar n=4 super Young-Mills theory. It's the simplest quantum field theory if you talk about interacting quantum field theories in 4 dimensions. And I don't think there's anyone in the audience that will try to argue with me on this point. So we've learned quite a lot from and about this theory and about ADS CFT through its integrability in the planar limit. So we've already heard a very pleasant introduction from David Gross, and also Thomas Klose had a more extensive introduction, but let me just summarize what we know. So we can by now solve the spectrum of local operators very conveniently, and dramatic advances have been made on the S matrix and on certain types of Wilson loops, and also correlation functions are now being developed. Hopefully, given a few more years, we can solve the theory in the planar limit for all other observables that we might be interested in. And that's not just a coincidence that we can do it, but that's the reason for that is very likely symmetry. So it's known that n=4 super Young-Mills has superconformal symmetry. A few years back, another superconformal symmetry has been observed in the planar limit, namely this T-dual superconformal symmetry. And if one takes these two symmetries, which are not the same, together, one obtains a very big symmetry, namely an infinite dimensional symmetry by the name of a Youngian algebra that governs this model and helps to solve it. Let me state a few more facts. This theory is UV finite. It has a planar limit. And the reason why I can talk about it is that it's related to ADS5 cross S5 strings via the ADS CFT correspondence. But let me go back to n=8 supergravity. In fact, that's a very similar theory to n=4 super Young-Mills for several reasons. One you've heard about in Henrik Johansson's talk. These are the KLT or BCJ relations that essentially tell you that n=8 supergravity is more or less 2 copies of n=4 super Young-Mills. I mean, that doesn't really apply to the final answer, so there are differences, but halfway through the calculation, you can still use the n=4 super Young-Mills results. And also, this theory is related to string theory in a different way. It's the low energy limit of string theory on a flat background. But of course, there are also differences. This is a gravity theory. It's Einstein gravity theory, which is non-renormalizable, probably. Moreover, there is no planar limit in this theory because simply there is no gauge group and which we could tune to a large rank. It has a different set of symmetries. It has n=8 supersymmetry, not superconformal, just plain supersymmetry. It has an SU8R symmetry. All these things are local. And then there is something new. It's a electromagnetic duality symmetry, which is an exceptional group E77. And the most pressing question about this theory is whether it's UV finite or not. And in the context of this talk, I would phrase the question as follows. Do the symmetries that this theory has, do they rule out all potential counterterms? And if there are no counterterms, then the theory must be finite, or UV finite. So in this talk, I shall discuss recent results concerning UV finiteness of n equals 8 supergravity, considering its invariance under this E7-7 duality symmetry, making use of scattering amplitudes from string theory, and also using representation theory of n equals 8 superconformal symmetry at the very end. But first of all, I would like to review what was known 1 or 2 years ago already. Well, in fact, Michael Green has explained many things already before, but let me give you my point of view, which is much the same, hopefully. So what we want to do in this talk is consider n equals 8 supergravity. That's this Einstein-Hilbert action with some supersymmetric extension. And we also add additional interactions to it with some couplings. And the question will be, which of these couplings receive ultraviolet divergences, and which of these couplings do we really have to add to the theory to make it consistent? And that is just taking loops from this bare Einstein-Hilbert action. The assumption in that is that we will quantize around a trivial flat supergravity background. So we can take the symmetries of this background into account. These are the manifest symmetries. They are manifestly respected, so there's really no doubt about them. Lorentz symmetry, flavor symmetry. That means if we talk about counterterms, these must be scalar and singlet counterterms. Right. In fact, when I talk, well, okay. And then, okay, there are the translation symmetries. They also are unbroken. They need to be respected. Well, bosonic translations, that's clear. Our counterterms must be homogeneous, so integrals over the whole four-dimensional space-time. Supersymmetry works very similarly, and supersymmetry is also manifestly respected. In fact, it doesn't really have a linear action on the space-time fields, but if later on we will be talking about scattering amplitudes, and there the action of translations will also be linear, so that's why it really has to be respected. And the last symmetry is the electromagnetic duality, and that really acts non-trivially or non-linearly. And so that's the question whether it really applies at the loop level. But this continuous E7 symmetry turns out to be anomaly-free, as was shown in that work, and that's really important for our analysis. But that just means we can rely on E7 invariance for the counterterms, for the construction of counterterms. Okay, so considering, first of all, just the Poincaré supersymmetry and the SU8 flavor symmetry, there are just a few counterterms that we can use. These have been known for quite a while, a few decades. Well, okay, this is just the Einstein-Hilbert action, and then there's an r to the fourth, d to the fourth, r to the fourth, d to the sixth, r to the fourth, and higher order counterterms. And they come all with different couplings. And actually, when I say counterterm, I don't mean that these will actually appear as counterterms to some UV divergence. I'm just calling them counterterms because they are singlet local operators and they might potentially be a counterterm. What I haven't made explicit in this is, well, first of all, you need to make them supersymmetric, so make a supersymmetry completion. So r to the fourth is not just an r to the fourth term, but it comes along with certain fermions and gauge fields and scalars. So it's anything between r to the fourth and d to the 8 r to the fourth. For counting purposes, you can say one curvature is two derivatives and a scalar, so that's equivalent. And there are many more terms. In fact, well, okay, I don't know how many, but there are just too many to write them down. But usually there's a unique supersymmetry completion. Furthermore, this is a nonlinear theory, so these counterterms need to have some nonlinear corrections. For instance, r to the fourth will come along with a phi squared r to the fourth and higher order corrections, but I won't write them down. And furthermore, this is just using Poincare supersymmetry in SU8, and this doesn't consider E77 for the time being. For counting purposes, or to understand where our counterterms may arise, at what loop level would there be the corresponding UV divergences, dimensional analysis is what you should do. Works as follows. At tree level, your action is just the Ricci scalar, which counts as two powers of derivatives, so it has mass dimension 2. And for every loop that you go higher, you have another 2 derivatives, so another 2 mass dimensions, which in particular means that at one loop you get mass dimension 4, which matches the dimension of space-time. So that's how the counting goes. And then we can write down the mass dimension of our first few counterterms, and we see that they arise at 3, 5, 7, 3, 5, 6, and 7 loops. And furthermore, some of these are BPS terms, whereas the higher ones are typically non-BPS. In fact, it makes sense to go to higher dimensions to get a better view of these counterterms. So you should start with supergravity in 11 dimensions and dimensionally reduce that to 3 to 10. And see where all these counterterms, at what loop level these counterterms may arise. So the counting is slightly different, that's why they would arise at different loop levels. Okay, so here I've shown what is known, what has been explicitly constructed. All these UV divergences have actually been observed in scattering amplitudes, whereas these few here have been seen to be absent, and for all these higher loops starting from 5, we don't really know yet. So that's the current status after these two works. And of course, when I have here are some fractional loop orders at which divergences may arise. That's just dimension counting where they would arise, but that really doesn't happen unless you understand what fractional loops means. So then we can compare these divergences, because there is a similarity between n equals 8 supergravity and n equals 4 super Young-Mills. We can compare to the UV divergences that one finds in super Young-Mills in higher dimensions. Well, certainly in 4 dimensions there are none. But in higher dimensions one sees a few divergences here and there. And when one compares, they actually look much the same. So mostly it's for 2 dimensions, well, 7 through 8, it's 2 loops where the theory diverges. It's the same here, except 8 loops, which is special. And then 6 here diverges at 3 loops, here also at 3 loops. So that really looks that these 2 theories are very similar and maybe the same. In fact, there are these formulas that tell you at which loop order the theory should diverge in which dimension, and they come from considering a special class of counterterms. So for supergravity, one sort of always picks the d to the 8 r to the 4th, and then one gets a formula like that. Whereas for super Young-Mills, one uses this line here, and that really tells you there are no divergences at 4 loops, but at higher loops you get some. Now, if you just look at the final results, as I said, the loop orders are very similar between these 2 theories. So you might be optimistic and see whether supergravity, the divergences in supergravity follow the ones in super Young-Mills. So does perhaps this formula also apply to gravity? And if it does, then it would be finite in 4 dimensions. So yeah, that would be marvelous. And if you look at that formula instead, then you would see its supergravity would be divergent at 7 loops. But going to 7 loops is very hard. even for those people. And so they thought about something else, what one can do, and consider instead 5 loops. And at 5 loops in higher dimensions, one can see that these 2 formulas give you different predictions. So for 5 loops, one would expect either d to the 8 r to the 4th to diverge, or d to the 10 r to the 4th to carry the UV divergence. And which means that it's either divergent in 4.8 dimensions or 5.2 dimensions. And well, when one doesn't see a divergence at 4.8 dimensions, then that would be really a nice hint that supergravity could be finite in 4 dimensions. But of course, you'd have to do higher loop calculations, and personally, I've only went to 4 loops in one case. Otherwise, all my calculations have been 1 loop. So what else can I do? And well, I'm a symmetry guy, so I'd like to think about symmetries. But one can also think about superspace. So these first few counterterms, they are all BPS, and BPS is always something very special, something that comes along with certain protectedness. There is, I don't know if it's a conjecture or fact, but all these BPS counterterms apparently can appear only up to 1, 2, and 3 loops. And in particular, they would not give rise to divergences at 3, 5, and 6 loops. So that if one could make this a Fermi argument, then this would establish that the theory is finite up to 7 loops. And indeed, at 7 loops, there is a first non-BPS counterterm that might carry the divergence. I'm very glad I put this reference here, but I'm sure I missed a few other ones, so excuses to those. So the questions that at this point I can put is how can we rule out these first 3 BPS counterterms, and can we rule out the non-BPS counterterm at 7 loops too? And then when we're there, are there other counterterms? How many are there? What are they? Can we rule them out somehow? And the clue to make progress is symmetry, and in particular, we haven't used E77 symmetry, but we can use it because it's anomaly free, and so we should. But what does E77 symmetry mean? Well, in practice, it usually comes in 2 parts. There's the SU8 subgroup, and that's just part of the R symmetry, and that's manifest, so we don't really need to care. Only consider singlets. And the remaining 70 generators that parameterize this coset, they essentially just shift the scalars by a constant amount. That's what they do in the linearized theory. So let's now consider these counterterms, d to the 2k r to the 4th. As I said before, you need to do the supersymmetry completion, and then you can also see some scalars. Well, if there are no scalars, then they are invariant. But in the scalar sector, they come with lots of derivatives acting on 4 scalars. And the curious result here is that every scalar is protected by at least 1 derivative. Whenever you see a scalar in this supersymmetry completion, it's covered by a derivative, and because it's a constant shift, it really doesn't, well, it's invariant under E7. But that's only true for the linearized counterterm in the linearized action of E7, but this is a nonlinear theory. The counterterms are nonlinear, E7 acts nonlinearly, and that's why it doesn't mean that these counterterms are already invariant under E7. There actually has been a recent claim that this E7 is strong enough to rule out all possible counterterms by a simple argument, and that has to do with the fact that E77 is a sort of electromagnetic duality, and one cannot really deform that duality. And if there's no counterterm, then the theory would be finite. But there has been another analysis of this, and which claims that you should be more careful, and if you really want to consider E77 symmetry at higher orders, you shouldn't require the counterterms to be exactly invariant under E7, but they have to be covariant in a certain sense. And if they are, then you can still write down counterterms with respect the E7 symmetry. But that's really all I have to say about that. So how to address this nonlinear symmetry? Linear can be done sort of easily, but how to address the nonlinear E7? Here one can make use of scattering amplitudes and unitarity. Point is that the scattering amplitudes, even at tree level, they come along with the nonlinear structure of the theory already. And we can use unitarity, construct the S matrix, and then generate these nonlinear corrections along the way. So let's consider scattering amplitudes. Okay. Right, so let's consider the various symmetries in the scattering amplitudes. First, there's supersymmetry, which we can realize linearly. Say in the spin-helicity framework, it's easy to see that supersymmetry really acts linearly, and it applies more or less this momentum conservation and supermomentum conservation prefactor, and a few more constraints, linear constraints from Q bar. So that's sort of similar, but E7 acts differently. E7 symmetry implies Adler zeros in the scattering amplitudes. And that means when you have an amplitude with scalar legs and you make the scalars to be very soft, that is, the momentum goes to 0, then along the way the amplitude should also vanish. So that's you just look at the scattering amplitude and you can see whether it respects E7 symmetry or not at this level. There's another consequence, which is not just single soft limits, but double or multiple soft limits. But so far, they haven't given rise to any constraints, and presumably they are governed just by the structure of the QFT or by unitarity. So maybe there's nothing new in that. So in principle, we could now go ahead and construct the S matrix. We shouldn't really start with the ordinary tree level, but tree level with these counterterms included. And then use unitarity or some sort of recursion relations to construct the amplitude. Well, we only need to go to tree level to see whether these corrections respect E7 symmetry, and by generating the right Adler zeros here. We could also use the BCJ relations and start with a calculation in n equals 4 super-Young mills, but also not plain n equals 4 super-Young mills, but we need to take these counterterms into account. But, I mean, in all of that, we need to include the counterterms, and if you want to do it in practice, that's tough, especially if you want to generate bigger tree diagrams. And a useful idea was not to do that, not to construct the S matrix from scratch, but use string scattering amplitudes instead. The point about string theory is that its effective action has all these counterterms already in, well, with a finite coefficient, and nicely so that these coefficients have, well, they are zeta function. So you can easily distinguish which comes from what counterterm. So we want to calculate scattering amplitudes in string theory. How does one do it? This is sort of a short recipe to do it. For convenience, you start with open string scattering amplitudes, because these are easier to obtain. You just have to compute a few, and then you can use supersymmetry to complete your scattering amplitude, make it supersymmetric, and that gives you the remaining components. But that was for open strings. Then you use the KLT relations to predict the corresponding closed string amplitudes. String theory is in 10 dimensions, so you would reduce it to 4 plus 6 torus dimensions. Now, the one remaining trouble with that calculation is that in string theory, you don't have E7 over SU8 coset, but you just have a smaller coset, namely this SO6,6 over SO6 cross SO6 coset. That is, in the E7 diagram, you cross out one node, so it's sort of, will be less constraining and will allow for more counterterms. Correspondingly, the R symmetry is not SU8, but it's actually SU4 cross SU4 and maybe U1. So how can we make any claims about E7 symmetry? Well, we can make some claims. Namely, if we just go to six vertex operator insertions, where 2 of them correspond to scalars and the other ones are just gravitons, then, well, having just these 2 scalars, we can do a certain averaging procedure to lift the 2 SU4s to an SU8. That works at least for 2 scalars. And then we recover the supergravity E7 over SU8 coset from it. When one does that in these scattering amplitudes, one finds that the double scalar, soft scalar limit is typically respected, while the single soft scalar limit is violated for all of the counterterms, for all of the first few counterterms. And that excludes the 3, 5, and 6 loop counterterms. I mean, in all of this, after this averaging, no trace should be left from the string theory. So that's why it's a plain supergravity result in the end. I mean, let me be a bit more specific about that. How is this E7 violated quantitatively? Well, if you look at certain scattering amplitudes, then you sort of start with the scattering amplitudes with few legs, and at some point you see that the single soft limits are not obeyed anymore. But what remains in this single soft limit turns out to be first a polynomial, that is, the violation is a local term. The violation of E7 is a local term. And only if you go to higher legs, then these violations will be rational functions, which indicate that there are some more propagator. But sort of the kernel of E7 violation will always be something local. And so this E7 violation really originates from the presence of counterterms. And quantitatively, we can say that these are the corrections, the nonlinear corrections to the counterterms, which then violate E7. In particular, because now you have scalars which are not protected by derivatives, then all these 3 terms will violate E7 symmetry, not at 4 legs, but at 6 legs in total. In fact, I should mention that this last counterterm requires some special attention, and that's because there are 2 competing contributions which both come with coefficient of zeta 3 squared. So in string theory, the lambda 6 coupling will be zeta 3 squared, which is the same as a quadratic combination of 2 of the R4 couplings. And that means when we start with a string scattering amplitude, we should remove this contribution from 2 R4 terms and to get the result of D6 R4. But in any case, all of these diagrams in the end have non-vanishing soft limits, so even this term will violate E7. These numbers we can cross-check with a different calculation using automorphic functions. So suppose our counterterms come with a certain scalar function attached to it. Then it was shown that these functions must satisfy certain Laplace equations, namely these, and the coefficients in these Laplace equations actually precisely match our results from string theory. In fact, this part of this Laplace equation here, which relates to this, really corresponds to this quadratic combination of 2 R4 terms. But what about 7 loops now? Okay, so at 7 loops, well, there exist many counterterms. There's first of all the d to the 8 r to the 4th, but also d to the 4 r to the 6th has the same dimension counting. In fact, there's 1 counterterm of this type at 4 legs. One can find 2 counterterms at 6 legs, and so on. And what about E7 symmetry? Well, if you do the string calculation in the same manner as before, you see that E7 is again violated at 6 legs from these terms here. You don't need to consider this composite things of lower terms here nicely. But at the same time, also these 6-leg counterterms, d to the 4, r to the 6, they also violate E7. And therefore, you can add to your d8 r to the 4th counterterms a certain linear combination of d to the 4th r to the 6th. And it turns out that in a sum, you can completely remove the E7 violation, and that tells you that you can find a nonlinear completion of d to the 8 r to the 4th, which does respect E7-7, at least at the 6th-leg level. So, but the question is, what about higher points? If you go to higher legs, can you still conserve E7? How many supersymmetric counterterms will there actually be at 7 loops? How many of those preserve the E7 symmetry? And is this one counterterm starting at D8 R4, is this actually equivalent to the superspace volume? So I'll try to answer those few questions. Now, the 7-loop counterterms, they are full superspace integrals, so they're not BPS. That means, well, your d to the 8 r to the 4th, you can write also as 16 derivatives acting on scalars, well, on 4 or on 6. 16 derivatives means 32 supercharges, and that's all the supercharges there are. So you would write them as full superspace integrals. And as such, they are manifestly supersymmetric by construction. In fact, they are non-vanishing when there are at least 4 legs or at least 4 scalars. And well, the only thing one has to ensure is that this is a scalar, this is an SU8 singlet. So for every SU8 singlet that one puts here, one can find a counterterm of this sort. And this is easily enumerated, so the scalars are in the 70 of SU8. So you take the symmetric product of n scalars and look for SU8 singlets in that tensor product. And well, that only works when n is even, so for even number of legs and up to 16 legs, I could determine how many singlets there are. This is the number, but it's clear that there are infinitely many counterterms at 7 loops, and in fact, all of the 7-loop counterterms must be of this form. That is because the BPS condition for singlets really doesn't work at 7 loops anymore. So it must be a full superspace integral of this form. How about E7 invariance? Now, to address that question, it makes sense to look at not singlet operators, but operators transforming in a 70. So because the single soft limit of any scattering amplitude, which is a singlet, must transform in the 70 of SU8. And the 70 operators you can also enumerate, and they have these multiplicities. You find that all the, I mean, it's obvious that the soft limits of phi to the n are non-vanishing, but when you add some supersymmetries, the soft limit of that might vanish, but it's not vanishing when you have more than 4 legs. So that is, for all of these, the single soft limits for 6 and 8 and 10 and so on, legs, they will not vanish, and therefore these counterterms will all violate E7-7. I will violate the unitarity bound soon. Okay, but the soft limit of the first one vanishes simply because there is no 70. That's because there is some conflict and there's a certain BPS condition, and that's why this one counterterm d to the 8 r to the 4 does respect E7 at the linear level. How about the nonlinear completion of that? Well, for 6 legs we have discussed it. There are there are actually two, well, it tells you that the soft limit lives in one of these two local operators, but we can compensate by adding one of these two, or a certain linear combination of these two. Now then you go to 8 legs, and there turn out to be 4 70 operators. That is, your soft limit must be in one of these 4, but there are only 3 counterterms to adjust for that. So does it mean that E7 is violated at 8 legs? And I really cannot take this argument away from you. So for that, it's well, we should look at the single soft limit as a constant shift of scalars. So when we have our counterterm, it's like a derivative with respect to the scalar, which is the same as taking an exterior derivative on the space of scalars, which is R70. And in fact, exterior derivative, you have the de Rham complex. So you should not just look at the singlets and the 70s, but also the antisymmetric combination of two 70s, which are these representations. And also we can list those operators which are supersymmetric. And now that's a nice argument by Guillaume Bossard. The point is that the single soft limit of an amplitude is a closed one form. The amplitude is a 0 form, so taking a derivative, exterior derivative, makes it a closed one form because d squared a is 0. And at 8 legs, the following happens. There is one 2 form, and this 2 form is exact because, it's trivial cohomology. So that means 1 out of these 4 is not a closed form, not a closed one form, but only 3 of the 4 are closed one forms. And that means that the E7 violation must be in this 3-dimensional subspace, and it can be compensated by adding or a linear combination of the 3 counterterms. And that's why you can indeed at 8 legs write down an E7 invariant. And if you go to higher legs, the reasoning goes the same. The point is really that the de Rham cohomology on R70 is trivial and there are no obstructions, and that means that this counterterm d to the 8 r to the 4 exists. So what is it? The claim is that it's the superspace volume. There has been a recent interesting result which actually tells us it's not the superspace volume because the superspace volume vanishes. But conveniently, they have also provided an alternative E7 invariant counterterm written in a harmonic superspace. And so at least that counterterm does exist. What does it mean? Well, it still means that 7-loop UV divergence is to be expected unless we know some other reason. And that other reason might be that this other counterterm, which is not the full superspace volume, is not a full superspace integral, and maybe one can rule it out by some other unknown mechanism, but presently we don't know how it works. So presently, I think we should expect a UV divergence at 7 loops. And unfortunately, I have to skip this section. Only show you this table. I've also, by computer analysis, looked at all possible counterterms, single soft limits, and obstructions, and one finds this long list of numbers, which might tell you something. In particular, it tells you how these BPS counterterms, which are here, these 3 BPS counterterms, at the 4-loop level, they are A7 invariant, but going to 6 legs, they fail to be invariant. And then I should really conclude. So we've investigated n equals 4, n equals 8 supergravity counterterms through SU8 averaged string scattering amplitudes, also using representation theory of SU 2.2/8. Well, that was mostly on the last 3 slides, and using cohomology of these representations. The results are as follows. There are supersymmetric counterterms. In particular, there are 3 BPS counterterms at 3, 5, and 6 loops. And when you go to 7 loops or higher, then there are infinitely many non-BPS counterterms basically at each loop order. However, when one takes E7 symmetry into account, all of these BPS counterterms get excluded, and only finitely many counterterms seem to be remaining at each loop order, starting from 7. So that means n equals 8 supergravity must be finite up to including 6 loops, and there's one counterterm at 7 loops where we don't know how to exclude it. So the outlook is, well, the only way to rule this out in my mind is that one finds some larger symmetry or some other mechanism to rule out this d to the 8 r to the 4th. And therefore, we would have to see whether n equals 8 supergravity is actually finite at 7 and higher loops, and why that would be. So there are lots of questions that remain. Thanks for your patience.
Okay, I think we have time for one question anyways. Edward.
So does your investigation of E7 symmetry shed any light about what behavior with respect to 5 loops? You said it would be fine.
All right. The trouble about 5 loops is, well, one would have to find, one can do the same analysis with E6 duality symmetry, and that would probably tell you whether all of the, I mean, the 3 BPS counterterms, whether they are excluded. I think by other analysis they are already excluded. So hopefully E6 symmetry in 5 dimensions would exclude those. Oh, 5 loops? Sorry. At 5, well, at 5 loops, one, okay, let's see. Where is this? Well, at 5 loops, the only counterterm that can arise is the d to the 4 r to the 4th counterterm, and that is excluded by E7 invariance. It's not E7 invariant in the nonlinear completion.
I wasn't asking if 5 loops is fine. I was asking how many powers of momentum can be pulled out in the foreground for 5 loops.
Well, this isn't actually about an amplitude, loop amplitude calculation that we did, so you should ask Byrne et al., but sufficiently many to...
I'm asking you because I want to know if you have any insight about what power of momentum will come out of the amplitude in 5 loops.
Well, okay.
After all, that's the next calculation that will be done. So.
Yeah, I guess I cannot really answer that, but... Oh, the question was, in a supergravity loop calculation, you have certain numbers of loop momenta flowing around in the numerators, but they can be rearranged to be on the external legs, and if they are on the external legs, they will provide less UV divergence. So Ed was asking how many of these momenta can I pull out, and actually I don't know the numbers, but I guess the claim would be just sufficiently many to ensure that d to the 4 r to the 4th will not appear.
But power counting d to the 4 r to the 4th won't be divergent until 7 loops.
It won't be divergent, not be logarithmically divergent at all.
My understanding is that you described earlier 2 possible extrapolations to higher orders. I think
To higher orders?
higher orders. They differ basically by whether the low energy expansion of the 5 loop amplitude has one number or another number of powers of momentum.
Okay. You refer to something I said at the beginning. This one. These 2 numbers. Whether they, yeah, okay. Well, I mean, the question is whether at 5 loops one finds this or that. With a divergence.
Finiteness corresponds to the one on the right. And although the 7-loop calculation won't be done soon, that calculation might be done soon.
Yeah.
If you had any insight to offer about what answer.
Right, but our analysis was only in strict 4 dimensions, so and using E7 symmetry. So one could do it, the analysis in 5 dimensions with E6. Maybe that will tell you something about it, but yeah. Right. If anyone can tell me how to treat that, what is it? 6.2 versus E5.8. Maybe that would help. Thanks.
Okay, so in light of the time, we should probably break here. We'll start again at 16, let's say 16:45.